So we're going to start chapter 16, which is all about traveling waves. We'll begin with section 1. And so a traveling wave, maybe the easiest one to picture would be waves rolling in on a beach. So those waves, you can see them moving, and that's the kind of waves we're going to look at. The way we're going to characterize the waves are, we're going to look at how fast does the wave move, how high are the waves, how far apart are the crests or the highest points of the waves. We'll also talk about how much energy is transferred as the waves move. So I would suggest at this point you hit pause in the lecture and you go read through section 16.1. It's not very long, but it's an introduction to the wave section, and it'll make sure you're up on all the terminology. Once you're done reading that section, then you can come back. Here's a video of one of my favorite kind of waves. This was taken in the Rogers Center in September 2015. All these games are playing again on Sportsnet called Blue Jays Rewind, so if you're interested, you can check them out. So let's take a look and then we'll talk about it a bit. So this is the wave. One of the things I want you to think about as we go through the rest of this chapter is the wave actually a wave? So in the next little bit, we're going to go through a discussion of what a traveling wave is and what describes it and how do we define it. I want you to take those definitions and descriptions, apply them to this traveling wave to answer, is the wave that we see at sports stadiums actually a wave? And that's one of the questions in your second written assignment. Let's start getting to the definition of what is a traveling wave. A very familiar kind of wave to most people is a wave in water. So in this simulation here, we let a droplet of water fall. We see that it makes a ripple, and the ripple spreads out all over the surface of the water. This is a side view, and now we'll switch back to a top view. The water drops and then the ripples spread out. Anybody who's thrown a rock into the ocean is familiar with these kinds of waves. So where we're going to go with this is, let's define what is a wave. Let's ask what's moving. Let's ask how is it moving. And let's talk about things like how do we describe it mathematically and things like that. So that's where we're going to go with the next part. Our definition of a traveling wave is that a traveling wave is an organized disturbance traveling through a medium with a well-defined speed. Okay, let's stop here. What do we mean by a disturbance? Well, if we think about that water wave that we saw on the previous slide in that little simulation, or if you think about making a water wave yourself by throwing a rock in a pond, then the disturbance is the ripples. I'm going to try and add that note here, but it's a little bit hard to write on my trackpad. Okay, so the disturbance is the ripples. So the traveling water wave is the ripples moving along. The traveling wave travels through a medium, and the medium is the substance through which the wave moves. So in a water wave, the medium is the water. So the disturbance moves by the water moving up and down. So let's think about that. Each little bit of the water, if we think about each ripple, so the water rises, then it falls, the next bit of water rises, then it falls, the next bit rises, then it falls. The water itself doesn't really go anywhere. You know, it moves up and down a little bit, but it doesn't move over a far distance horizontally. So what actually moves? So when the wave moves, what is moving? Let's think about if you're standing in the water on a beach and a big wave comes in, you can almost get knocked off your feet, right? So the thing that's moving is energy. So energy is the thing that's transferred in a wave. A wave carries energy. So there's our definition of a traveling wave. It's a disturbance traveling through a medium, and the disturbance is the energy of the wave. The two kinds of traveling waves that we have are mechanical waves and electromagnetic waves. A mechanical wave is a wave that moves through and disturbs a medium. Some examples of mechanical waves are sound waves, waves in water, maybe a wave on a string if you strike a string up and down. In our mechanical waves, we need to have a source to start the wave. For example, to start a wave in water, you have to throw a rock in the water. So the rock is the source that starts the wave. And the wave propagates by some physical interaction between the elements of the medium. So in a water wave, each water molecule, as it's been disturbed, pushes the water molecules next to it. So as they push on each other, that's what propagates the waves. So that's our mechanical waves. We need a source, we need a medium, and we need some sort of physical interaction to propagate the wave. Electromagnetic waves are super interesting. They can travel without a medium. So an electromagnetic wave are oscillations of electromagnetic fields, and we're going to do lots more of that a little bit later on in the course. Electromagnetic waves, even though they don't disturb a medium or propagate through a medium, they still transfer energy, and you can feel that's true if you go outside and stand in the sunshine. You feel the warmth, the heat energy traveling from the sun. So it comes from the sun and it reaches us. It travels through the vacuum of space, but it still gets to us. We're going to start chapter 16 with mechanical waves, and then after we've done a nice long discussion about those, then we'll move on to electromagnetic waves. There are two kinds of mechanical waves, transverse and longitudinal. A transverse wave, the one you see there, is where the parts of the slinky move up and down, but the wave itself moved to the right. So that's a transverse wave. When a piece of the wave, here it is now, that's transverse, piece of the slinky moves up and down, but the wave goes to the right. The other kind of wave is longitudinal, and that's this one right here. That's where the pieces of the slinky move left and right, but the wave itself moves to the right. So that's the difference. In a transverse wave, the elements of the medium move perpendicular to the wave. In a longitudinal wave, the elements of the medium move parallel to the wave. And then important to notice, in both kinds of waves, overall, the slinky doesn't go anywhere. Elements of it do move for a little bit and then they go back to equilibrium, but the slinky overall doesn't go anywhere. The wave moves down the length, but the slinky itself stays put over time. So our two kinds of waves are transverse and longitudinal. The transverse has motion perpendicular to the wave, and longitudinal has motion parallel to the wave. Here's a summary of our transverse and longitudinal waves. So our two kinds of waves are transverse and longitudinal. In transverse waves, the elements of the medium, here I have a wave on a rope. In the video, it was a slinky just because it's a little easier to do. In transverse, the pieces of the medium move perpendicular to the disturbance. An example would be waves on a guitar string. For a longitudinal wave, the elements of the medium move parallel to the disturbance. So there's the two big differences. For both of the waves, the wave speed, that has a symbol of a lowercase v. The wave speed v is the speed at which the disturbance travels. Okay, so it's the speed that that pulse goes down the rope or down the slinky. That's what a wave speed is. How fast does the bump travel? There are going to be some different ways we can calculate it. And one way would just be to measure how far does it move and how long does it take. That'll be something you'll use in solving some of your problems. The next thing we want to move into is a mathematical description of the wave. For our mathematical description, the first thing we're going to aim to do is describe what is the height of a piece of the string as a function of horizontal position and time. So we're going to look at a pulse on a string to start with, like we have in the picture here. We're going to say that the pulse is moving with a wave speed v, that's moving to the right along the string. And we're going to ask, what does the height of that piece, what does the height depend on? And we're going to look at how we build that equation and that description. So the first thing we'll do is let's draw a pulse on a string. So I've just got a long string and I put a pulse on it. The next thing we do is let's pick out one point on the string. So I picked one point and I just marked it with a red dot. So here's my point on the string right here. Marked it to a red dot, and what I'm asking is what happens to the dot. So to get into our description, at this point in the picture, the time is t1. The height of this piece of string, we're going to call the height d. A lot of textbooks, probably every textbook except the one that we have, would call this height y. So if you're talking to the people in the help center or using a different textbook, you might see it as y. Our textbook uses a d, so we're going to stick with d. We're going to ask, what does that height depend on? So this height means d. Okay, what happens to that height over time? What happens to the height of that dot over time? We're going to develop this description for a pulse on a string, but it is true for all kinds of waves, longitudinal, transverse, mechanical, and electromagnetic. So the kind of description that we end up with is going to apply to all waves, but to visualize, we're going to look at a pulse on a string. Okay, so here's our wave at time t1. This wave, remember, is moving to the right with speed v. So let's ask what happens to this little bit a little bit of time later. So before you go to the next slide, why don't you try and picture in your head or even draw on your paper what happens to that bit of the dot. So in the next little bit, we started right here. So this is where it started. The wave has moved to the right. So where it ends up is the wave has moved over a little bit and that little piece of string has moved up. So the little piece of string has lifted a little bit of time later. Okay, let's move a little bit of time later still, and you try to predict what happens first. So a little bit of time later still, so we started here, and it moved along, and it moved along some more. Started right here with this dot, it moved up a little bit, then the peak goes past, and it's starting to fall. So it reaches the peak, and now it's starting to fall back down. So it's at a different height. In the next picture, a little bit of time later still, the wave is mostly gone, so it moves along here, along here, along here. Now the pulse is pretty far past. Now that little bit of string, it's almost back to equilibrium. Let's look one little bit of time later. So a little bit of time later now, it's gone back to equilibrium. Oh, it's so hard to write on a trackpad, but I think that's an important to write down. So back to equilibrium where it was before that pulse passed by. So that's where it is an amount of time later. So we're going to want to develop the description for the height of the wave. And what we've seen is the height of that piece of string, that element of string, it lifted, then it fell. So the height of the wave depends on two things. It depends on where it is horizontally, because if we had picked a different horizontal position, we would have gotten a different height. And it depends on what time it is. So the height of the wave d depends on, so the height of the wave d depends on the horizontal position x and the time t. So when we write that down, we say d is a function of x and t. The parentheses here don't mean we're multiplying d by x and t. It means that d depends on x and t. And d is the height measured relative to the equilibrium position, which is where the string is lying flat. So the next thing we want to do now is move on to writing an equation for d where we can calculate what d is. That's going to be our next part. So before we move on to writing the equation for the height of the string as a function of horizontal position and time, let's first ask a conceptual question just to make sure we have the idea. So let's have a wave on a string. Let's say that our wave is traveling to the right as in our picture. At this instant in time, let's pick a dot that's at the middle height. So let's pick the point that's right here and ask what happens to this piece of the string at this instant of time. So is this dot, is it moving up? Is it moving down? Is it moving to the right? Is it moving to the left? Or is it not moving at all? So that's a good question. Try and predict what the answer is. Hit pause here, really think about it, and write down your answer. Committing to an answer is really important, so you have to choose your answer before you move on and see what the right answer is. So if you're having some trouble trying to sort out exactly what the answer to that question is, you can try using a simulation to help you see it a little bit better. You could try drawing the wave as it progresses, but a simulation is a nice quick way to do it too. If you want to set up the simulation for yourself, you can Google PHET, P-H-E-T, wave on a string. So you should get some sort of a wave window pop up. If you pick the settings for oscillate, no end, no damping, and about a medium tension, you should get a simulation that looks like mine. And then arrange it so that you have a dot at the equilibrium position that looks like the picture we had on the previous slide. So what we're asking is, as time moves forward and this wave moves to the right, what happens to that little green dot? Does it move up or down, left or right? Let's play the video and let's see what happens to it. So we see that it starts to move upwards. So these simulations can be really nice to help you out if you're having trouble visualizing it. So the answer to our question, the wave on the string, which way does that dot move? The answer is up.